Dr. Feng has over 14 years of industry experience prior to joining the university at UT Austin. Specifically worked at PharmaForum, where actually we met for the first time. And as a matter of fact, that was one of the very first places where they ever offered GMP hot melt extrusion as a CDMO, which has become much more common nowadays. But Professor Feng has continued, Professor Zhang has continued his work with specifically extrusion and hot melt extrusion. More specifically today, he's going to talk about long-acting injectables and implants that can be manufactured using similar process. And as a matter of fact, that is also a continuous manufacturing process. So it's my pleasure to turn over the floor to Dr. Zhang, and please welcome him on the stage. Thank you.
All right. You guys hear me okay? Okay, perfect, yes. So about 5 years ago, I started doing a lot of long-acting implants. Doing like oral delivery system at university, you will never survive because funding is just not there, right? When you start doing long-acting implants, it gets really interesting. You're working a lot with people doing the drug discovery. So this particular here is on the PLGA-based long-acting implant. The research actually is funded by the FDA. So, there are many long-acting PLGA-based products, but there's actually very few generics. And part of the reason actually is PLGA is a very complex polymer, right? And what FDA is interested in, how does PLGA blockness impact drug release? When you make PLGAs, you start with glycolide and lactide. But glycolide is very reactive. Like there's a reactivity ratio. So it goes from GG first, then lactide inserts in. That's how PLGA is made. Right? It's not by condensation reaction. It's for ring opening polymerization process. So then there's a material attributes difference. Somebody can give you PLGA, but if they have different LG blockness, in theory, drug release can be a lot different. If you're very blocky, initial degradation is fast, then you slow down. If they're totally random, it's more even degradations. So how does that impact drug release? Now to do this, we selected, this is actually a collaboration between me and there was Professor Nate out of Chemical Engineering Department. All he does is reaction kinetics, right? So his claim is famous. If you give me a PLGA, if I know the blockness, I can tell you the synthesis conditions, the temperature, the reaction time. Now to do this, we teamed up. We select Ozdex as a model because FDA is interested in understand Ozdex as well. The reason we select Ozdex because it's continuous manufacturing made by the extrusion process. That's what I know very well. You cannot do microspheres because the process is so complicated, right? For us to look at minutiae difference in the PLGA blockness, the process has to be so well controlled. That's what we did. So let me go back, let's see. So dexamethasone has been on the market for a long time. There's no generic. And this is used to treat uveitis. So when we do this project, we actually had a medical doctor who is focused on uveitis at UT Dell Medical School. So actually has a very, very interesting experience working with them. And this is made by the extrusion. It was original by Allergan, and that's part of AbbVie. So the formulation actually is very simple. You got dexamethasone-free base, and you got two different grades of PLGAs. And the difference in the PLGA is acid-terminated versus ester-terminated. And that actually makes a difference in the drug release, okay? To understand, we also know to look for even with dexamethasone implants, to investigate PLGA blockness differences, our process has to be very tightly controlled. I can't have too much variability in my process. And later on, if that process is too variable, you can't investigate the variability in the raw material, right? So we spent lots of time to understand the process. And the key question we're asking is, how does PLGA variability impact dexamethasone, both in vivo and in vitro? But prior to that, we had to understand like formulations, how do you control them? Is PLGA stable, right? How does dexamethasone release? So Ozurdex actually is a two-phase system. You have basically dexamethasone dispersed in the PLGA, and dexamethasone retained as a crystalline. There's very little interactions between dexamethasone and PLGA. Dexamethasone is a high melting point, okay? And we have done the studies to understand if there's any solubility at high temperature. There's not. Dexamethasone does not dissolve, just simply being dispersed in there. And the surface is very rough because it has a high solids content. This has a lot to do with rheological properties, which I'm not going to get into. And you actually can control the surface roughness. We worked on the system where we can control process temperature. We can dissolve drug in there or disperse drug in there, and then you get totally different implants. So here's dexamethasone. This is a micro CT scan. And if you look at the surface, is very rough. Also has lots of pore in there. Right? We introduced this concept, internal porosity and the total porosity. There's many ways to look at roughness on the surface. We actually like this total porosity because when you make the implants, you use a laser gauge to measure. And laser actually casts a shadow. That shadow actually factors in the surface roughnesses. So you can have the same diameter based on the laser, on the shadow. But depends on surface roughnesses, actually you're getting different materials. But that's what we had. And then the key thing making the implants is dimension control. That dimension has to be extremely tight, right? To do that, your material has to absolutely flow. So what we did a two-step extrusion process. We did this, I have a video here. First step, we just basically mix them together. We don't really use a dye. Material goes through, we make large rods, and we break them down to fine particles. The material has to flow. Actually, when we first do this process, because in the lab, sometimes you don't have all the precise humidity control. We're so scared about PLGA degradations. So I'm not presenting that data. With low molecular PLGA, as long as your starting material is less than 0.1% moisture, you don't worry about degradations. They're actually very stable. After the process, you lose about 10% molecular weight. Okay, it's quite stable. So then do second step extrusion, then you cut. So here's the video. Can you play this video? So this is actually the second step extrusions. We already made the granules. That's on the feeder on the top. Okay, we're using Haka Mini Lab. We're running 10 grams per hour, very slow. The dose is very low. We can't feed everything at the one time because PLGA has low TG. If you feed too much, you're going to choke the feeder. And then second step extrusion, we're processing about 110 degrees C. The stuff come out. This is the guided plates, goes through laser gauge. And this is puller. We worked with a company in California, made this custom-made puller. It's a special puller. And we have this very consistent diameter. So, in a commercial process, you may want some feedback loop, right? But here, we can't afford it. But we can control this very precisely, okay? So the feed rate is mainly controlled by the RPM of the Haka Mini Lab. But we have another step using the twin screw to feed, to control, to have a little bit choking effect. But we can get very precise control. And we have shown different graduate students, different days. We don't really try to do it when it's too humid. Okay, but it's actually very consistent. And this actually matched up published data on Ozurdex. So Ozurdex, and this is actually done in the normal saline. Okay. Early on, we do normal saline because normal saline gave us about a month dissolutions. Not in the normal. If I do in the PBS, right, phosphate buffer 7.4, that's more bio-relevant. And that round will go over 3 months. And I can't, it's hard to do a research when you don't get feedback every 3 months. So done this, we're actually very proud. It took us about 9 months to really figure out this whole process. So now if you look at the drug release, the three phases, initially very few drug gets leaked out because implants, unlike microspheres, has a very low specific surface area, right? Plus dexamethasone is not dissolved, actually it's dispersed. So there's very little burst release effect. And then after that, release over 3 weeks. We talked to Dell Medical School doctor. They said, we asked them, we go like, so once you put implants in, there's no effect? They said, no. I put implants in this morning, by the lunchtime, I already see the effect. So, dexamethasone has a very interesting PK, PD correlations. That's actually another layer of complexity. But apparently, we found out later, for dexamethasone to be effective, you actually need very, very low level of dexamethasone concentration. What we see here, this burst, if somebody can develop a dexamethasone implant, has just released like initial, like first 7 days, very low release rate, that would be perfectly effective. Actually, later release burst create side effect, create high ocular pressure, okay? But so why do they release drug this way? So we did this whole test, and we monitored several things, right? We monitored the PLGA TG, wet TG, okay? We look at the drug release, we look at the weight loss, polymer molecule, we look at how does polymer degrade, right? We look at, and then also moisture uptake. So if you look at this table here, we go through day 0 to day 27, right? You find out, even at this one here, like even at day 7, we already lost. We already lost 56% molecular weight. But drug release is only 2%. Right? Even though PLGA degraded, but drug is not releasing. And so what's going on here? So I'm going to click through several videos. So this is, right, this is day 4. And day 7. At day 7, still very low drug release, but implant structure already changed. So even though PLGA is not water soluble, but water does ingress. And once the water goes in, PLGA starts to hydrolyze. And once they're hydrolyzed, it's self-catalyzed, right? Because when PLGA degrades, ester bond breaks to the alcohol and the acid. PLGA degradation is pH dependent. The lower the pH, the faster the degradation is. So, but then on the skin, there's a difference, right? If you look at the skin effect, obvious, right? 14 days. 14 days, that's where so drugs start releasing. Look at 21 days. You see the difference in the skin and the core. Because in the core, there's a acidic environment. On the skin, you get buffered. Even though we're on the normal saline. We run the distal in the normal saline, the immediate pH is about 4, 5-ish. Now, if we start thinking running the phosphate buffer, the skin gets protected even more, right? pH 7.4. So you actually have a difference in the skin versus core. When they first degrade, they degrade to lots of oligomers. And those oligomers cannot really diffuse out until they drop to certain critical molecular weight. Sipperman group in Europe did a lots of study. They find out there's a critical molecular threshold when those oligomers actually can really dissolve and diffuses out. So we're dealing with this skin and the core phenomenon. And that's what's caused this unique phenomenon where polymer degrades, but drug is not coming out until much later. At day 28, most drug is gone, and you still see the skin effect. Now, at this point, the skin is very porous. Okay. So I was telling you earlier, if I run this distal in phosphate buffer, it's a 3 months distal testing. Right? Because now you get this even more dramatic protective effect by the dissolution media. So going back, while we're doing this study here, we're really trying to understand how does PLGA blocking this affect, right? So with Nate's group, they are looking at those reaction kinetics, and based on reaction kinetics, we worked with Akina, Akina Parks company out of West Lafayette, Indiana. We gave them those reaction conditions. We want them to make PLGA of different blocknesses for us, right? And we also had Evonik. We bought 2 different lots from Evonik. This is actually 1 year apart from Evonik, which is commercial supplier for PLGA they used in Ozdex. And we mainly focused on acid-terminated PLGAs. This is the primary components, okay? So we went ahead and made, custom-made different blockness, and then we used 2 different lots of Evonik PLGA as a control. Let's see what happens, right? So, we're trying to match up as tight as possible in the molecular weight, LG ratio. I brought up this residual monomer and acid numbers. This actually is very interesting because, when we do the extrusion process, those material gets left behind. If you do a microsphere, that gets washed away if I have residual monomers. This actually is one difference we realize later. For the extrusion, whatever you have, most likely they stay. Okay. As a matter of fact, one thing I did not explain to you, why we have those pores, right? Those implant has pores. So for the extrusion, I used to do AST, and material we got, we never have pores. Those pores just because air entrapment. Because we use hot convection lab, we actually don't really vent. There's no vent systems. So when the air gets trapped in, PLG has a very low TG. When the air gets trapped in, those pores stays. And we actually have a way to control the porosities. If I make the die or the process temperature change, I can make the front side more restrictive. The more restrictive they are, my pore gets smaller. So this is a way to control. We can control from 5% all the way to 25% porosity. Right? So, and this actually was later on was after fact. We realized, oh wow, with the extrusion process, whatever your starting material is, most likely end up staying, and they will impact drug release. So let's look at the drug release. Normal saline, they're all the same, right? If you look at the PBS, those two, this green and red, those are 2 different batches from Evonik, a year apart. 2 different students did it. And this is actually very consistent. We're looking at release over 3 months, right? This is more blocky, and this is less blocky. If I don't look at Evonik material, this actually sort of trend what we originally thought. More blocky ones, drug release is faster. Less blocky ones it's a slower drug release. And one of the questions is why at that time, we're puzzling. So we look a little bit closer, we find out with more blocky ones, the implants actually will split during the dissolution test. We believe the reason is because the difference in the residual monomers and higher acid values, okay? And that's what's caused. There's an osmotic effect, right? When the polymer degrades, they become oligomers, but they cannot diffuse it out, so water wants to come in. So implants will swell to some extent. And, and they can cause rupture of the implants. So one of the questions we got was, let me go back to this. Is there actually difference? Oh, sorry. Is there a difference in vivo? Right, like this one is released really fast, and compared to, so we use the faster release profile compared against the one Evonik-based material implants. So we did Rabbit Eye. Rabbit actually is a very good model for the intravitreal implants. And 2 formulations. A, that's Akina polymer, E stands for Evonik. And it's kind of interesting, and this has been published, Ozdex by Allergan. So we did a rabbit study, we can retrieve the residual implants. We actually look at how much drug is released in vivo, right? And if you look at this one here, this actually matched up pretty decently well with published data. Now, of course, Some of the study detail may be different, but we're going like, wow, this actually matched up decently well. And we also look at its metabolites. So 6-beta hydroxy dexamethasone is active metabolites of dexamethasone. So we can look at, there's 2 ways to look at the data. When we do the rabbit, one eye has a control, which is evonik material. Another one has, we call sample, the test samples, which contain polymer made by Akina. So you can group left eye all together and group right eye all together, compare the difference. Another way to do actually is do paired analysis. You can look at single rabbit, left versus right. You look for the difference, right? And statistically, they're not really different, and the difference within the confidence interval, except this 21 days. But we're all doing the group of 6 rabbit. And we think if the group size gets bigger, there's probably not much different, okay? And what's really interesting is in vivo, in vitro, release-wise, normal saline actually is a better predictor for the in vivo release, even though it's not bio-relevant because the vitreous environment is pH 7.4. Okay, but release-wise, they match up really well. And so so there are several reasons. We went even one step further. We're looking at polymer degradations. Okay, look at polymer degradations. Molecular weight decrease in the normal saline actually matched very similar to what's in the rabbit eye. Okay? So one of the questions is why? We believe one of the fundamental mechanisms is how does those oligomers diffuses out? Because those oligomers play a very key role, right? They create a low pH environment, which triggers all these degradations. But what happens in the eye, it's not just water, all right? There's a network of collagen fibers and hyaluronic acid. They actually slow down the diffusion of oligomer. We believe one way to do in vitro distal for the vitreous implants actually to run in a viscous distal media. Don't run just in the water. Like if I run the phosphate buffer, high viscosity, you can have the polymer in there to slow down the diffusion of oligomer. That may be bio-relevant and also bio-predictive. So here's the key learnings. I'm not going to read all these details here, okay? But all our study has been published. Early on, we did a study to understand the degradation kinetics, PLGA during the processing. Okay. It's about 10% drop in the molecular weight. But the way we made implants, the material is in the extruder for 40 minutes. This is totally new learning for me as well because I used to do ASD, material flying out, 30 seconds, right? But this is very, dimension controls, the residence time is very long. And we also had a study about, PLGA variability in the manufacturing process, drug release mechanism, reverse engineering of the Ozdex implants. This is really, this is a study, one of the studies I'm very proud of. So, and again, I want to thank, this project was sponsored by the FDA, this whole study. And my collaborator, Nate, out of UT Chemical Engineering, and then the physics and geology department, they helped us with some of the image analysis. Thank you.
Thank you, Feng. Wonderful. All right, so we're going to take a quick networking break next door now. Head over to the Garden State Ballroom. We're slightly behind schedule, so we're going to reconvene at 11:20 for our next speaker. So we've got about 25 minutes. Head next door, grab yourself some coffee, refreshments, meet with the exhibitors. We'll reconvene for our next session at 11:20. Thank you.